Thank you. Not my words, but I appreciate the sentiment. So, so this is some work that I did with my colleagues Joshua and Gabriele. In a functional language like Haskell, we have these algebraic data types. Here I can define a singly linked list like this, and I can write some kind of function over this by pattern matching on each of the constructors, right? So this is sort of bread and butter for functional programmers. I don't think this is a controversial thing to say that, this is quite nice. And I think the evidence is there that, it's a good thing because other languages have started to steal these ideas, right? So we have these algebraic data types and we can write functions by pattern matching on the constructors. And so that's nice. And so there's another thing that you can do with that then, right? So I can write this thing called an embedded language, where what I'm going to do now is define a data type. I'm using GADT syntax now, but same idea. But I'm defining a data type now, and then the constructors of my language are going to be the terms in this embedded language. So like the things that I can do in this embedded language. So I have these two constructors here. The first one is just introducing a literal value into my embedded language. So I give it a thing of type int, and I get an expression of type int out, right? And then the successor constructor, which should add 1 to an expression of type int. Yeah? And so I can write terms in this language by just kind of building these constructors together, right? So I can write some expression here. So this is an expression that when evaluated will give me an int. And that's built up by just directly using the constructors from this data type, right? I'm directly using the terms of this embedded language. So I can build like terms in this language, and then I can write an evaluator for those terms, right? And the same idea, right? I can just pattern match on the constructors of this data type and then do the thing at each constructor, right? When I get the literal term, I can just return that number directly, right? So this is a nice thing, right? So I have algebraic data types, I have pattern matching, I can write functions over these data types, right? Pretty standard, yeah? And if you're at my talk at Haskell Implementers Workshop, you might remember, like I actually just stole this slide there as well, right? So I also had to talk about embedded languages, and so I've just kind of stolen that slide. But there was another thing that I didn't talk about here, right? So GADTs are this thing that's been in Haskell for a while now. And writing these kinds of embedded languages is sort of the canonical example of why you want to use the GADT. And in their example here, they have this constructor pair, which is quite nice, right? I give it a term of type A and a term of type B, and that says, oh, this is the same as having a term of pair AB, right? Which is kind of nice. And in this example, they don't really tell you how to use it, right? You can't do anything with that. But it kind of gives this nice hint about, maybe we can do something with data types as well in these embedded languages, right? Maybe I can have pairs in my embedded languages. Maybe I can have other stuff as well. I don't know. So what about if we had embedded languages with algebraic data types, right? Like we started with this idea of having algebraic data types, and I can write nice functions on them. I can build an embedded language using algebraic data types and pattern matching. But, it's totals all the way down, right? So why can't I have an embedded language that also has algebraic data types and pattern matching in it, right? Like, why can't we have both? Yeah. So this is the problem that we're looking at in this work, right? So can we have a deeply embedded language, like the thing I described before, that also supports user-defined data types, as well as pattern matching on those algebraic data types. Okay? So this is the key thing that we're trying to tackle in this work here. Trying to bring things full circle and have embedded languages with the same facilities that made it so nice to write those embedded languages in Haskell in the first place. So I've been working on this project called Accelerate for a while now. So this is, again, this giant GADT. It does the same sort of idea, right? And so there are different ways you can try and achieve this. So in Accelerate, for a long time, we had this idea of lifting constructors. So I can define this thing called lift, and it essentially tries to push the constructor through this, the terms through this constructor, right? So if in this pair function here, I give it two expressions, one of type A and one of type B, and I want to sort of lift the pair constructor through that somehow and get an expression of pair out, right? And then you might want to do the opposite thing, right? So given an expression of pairs, I want to sort of pull out each of the components, right? I want to push that pair constructor the other way and get a pair of expressions out. Right? So you can do this, and it sort of works, and then you run it, and you'll get a nice type error that mentions all of this sort of internal stuff, right? Which is not very nice, you know? So even if we have the Haskell error code index, and I can link directly to that, like, it's not a very pleasant experience, right? Like, this first function should just work, right? So that's not very nice. So, you know, one option is this, right? A second option is, you know, just don't do that, right? If that's problematic, let's just avoid that problem, right? So instead of trying to have expressions of pairs, how about we just sort of leave everything in unlifted form, right? Always have pairs of expressions floating around, right? And so this avoids this need to sort of lift and unlift terms, like push this constructor through our expression type somehow. And it simplifies some other things, but then it does sort of introduce other problems, right? So it relies on compile and magic to remove some redundancy here. And, you know, that's not always possible, right? So, and even if you do that, right? So there's also a subtle limitation with both of these approaches in that it only works for polymorphic containers, right? It works for pair because I can have an expression of pairs, but also a pair where each of the components are an expression, right? But if I have something like this data type point, there's no way I can kind of, like this constructor point, sorry for the punning, requires things of type float, right? I can't mash an expression of type float in there, right? This is fixed, right? So there's no way to kind of lift and unlift terms of this type that's fixed. And then the further thing, right, is that it doesn't support some data types. And so typically you'll have some types that are just sort of built in. So Boolean, true and false, that's built in. And then I'll give you something to do conditionals on Booleans. And maybe if you use rebindable syntax, that looks nice. And if you're lucky, maybe you can support like a maybe data type, right? And then I can write a combinator function like this that is sort of magic, but it knows how to deal with this thing, right? And I try and convince you that, like, yeah, it works, but it's not very nice in practice. But luckily, this morning, David was kind enough to make this argument for me, right? It says, like, you know, how do functional programmers actually write code? Well, they prefer pattern matching instead of using combinators like this, right? So thank you very much. And so this is what we want in this work, right? So how do we have pattern matching in the embedded language? All right, so if we're talking about how do we have pattern matching in an embedded language, the first thing is we need some kind of language to talk about. So this is just going to be the language that we'll use. It's just a standard lambda calculus, but the things that we add to it, so we need some way to encode an idea of data types here. So here we're just going to use a sum of products style representation and just represent everything as nested pairs of stuff, right? So this is the only kind of data types that we're adding to this language. And then we're going to need some way to do case expressions on this, right? So these are just these two things, right? I need some way to represent data types. We're just going to use nested pairs for that. And then this special thing here that we'll get to, of course, like how do you do case expressions in this language now, right? We need to somehow lift the case of from Haskell into our embedded language somehow, right? That's the core of this. All right, so if we come back to our data type point here, right, how do I represent this in my embedded language? So we have this data type point, right? This is the user's data type, right? So this is what I'll call the surface type, right? These are all of the extensible types, right? I don't want to change my compiler every time a user wants to add a new data type, right? So I need to somehow map that into a representation that my compiler understands, right? A sort of normal representation, right? And so we do that by representing everything as nested pairs, right? So if you think about this data type point, the only interesting thing is it has 2 floats in it, right? So I'm just going to store that information around, yeah? So this is my representation type. And my compiler knows how to deal with representation types, and because it's always in the same format of nested pairs, that can be closed. All right. And so now I need a way to kind of build one of these things, right? So I can write this function build point, given 2 expressions of type float, then I need to kind of get a thing that looks like that representation type, right? I'm just going to put this into this nested tuple, right? So I'm going to put it into a tuple where it's just like I'm using pairs as sort of a list, right? The pair constructor is my list cons, and then the unit is my list nil, right? You can kind of think of it like that. Yeah? But I'm just taking my x and y, and I'm putting it in this representation that's nested pairs, right? And then when you want to do the other thing, right? How do I project out each of the components of this thing, right? Then I can return 2 expressions, one that projects out the first component and one that projects out the second, right? So note that this is a Haskell pair of embedded expressions. So it's a bit small maybe, but at least for the people that are not colorblind, I'm going to use the blue color in types to represent here's an embedded term, right? Here's an expression level thing. And then red is going to be Haskell level things, right? But if you can't see it, you just have to think a bit harder. Sorry. All right. And so, we're just given some expression P, we're just going to project out each of the components by adding new abstract syntax on top of that, right? And I return these 2 other expressions. Right? So that's how you do it, right? We're taking this surface type, this user's type, and kind of mapping it down into this canonical representation as this sort of sum of products style. Okay. So we can get these data types into our language now. How do we use them, right? So the second ingredient is to make heavy use of pattern synonyms. So pattern synonyms, this great great extension that allows programmers to define new patterns, right? So pattern synonyms exist in the same namespace as constructors. So I'm just going to put an underscore after the name to say, oh, this is my pattern synonym now, right? So I can write this pattern synonym now, and it's going to look a lot like the type of the constructor, right? I'm going to take 2 floats, but now 2 expression floats, and return an expression point, right? So pattern synonyms consist of 2 things. There's a builder. So this is the function to run when I use this thing as an expression, right? So when I want to construct a thing of type x point. And then the second thing is the matcher. So this is the thing to run when I'm doing pattern matching. So when it's on the left-hand side and I want to destruct one of these things to get the x and the y out. So this is bidirectional pattern synonyms, explicitly bidirectional, right? So I'm running a different function on the constructing and when matching, right? And these use the definitions from the previous slide, right? So these are just functions that will kind of piece together the abstract syntax of my embedded program as necessary. Right? And so that works well and good, right? And so now with this pattern synonym, I can write code like this, and it's going to look a lot like it would look as a regular Haskell program, right? Like on the left-hand side, I can use pattern matching on point underscore now to get the x and y out. I can do things with my x and y, and then I can wrap it up again in a point using the constructor on the right. Yeah. So this is this really nice feature, right? So I can use my pattern synonyms now to write embedded expressions that look a lot like regular Haskell, right? So can we just kind of continue the same thing, right? So can we extend this to support some data types, right? How can I, this maybe combinator that I had before, instead of having kind of deep compiler magic and having that baked in, can I just implement it in the standard way, right? So can I just have a case here that now I have my constructors with this magical underscore that does the right thing, right? Can I implement this maybe function like this? And then the answer is this is not quite complete yet. So we're very close, but there's something missing, right? And so the problem here is one of staging. So if we're thinking about what does it mean to run a deeply embedded language? If I have my Haskell code, right, the standard way is I take this Haskell program, this Haskell source code, I run it through GHC, and I get some kind of executable or object code out, right? So this is the Haskell compile time. And then separately, I'm going to run that program, right? And so when I'm running my Haskell program, this is the time when I'm generating this abstract syntax tree that represents my embedded program, right? And then once I have that abstract syntax tree, then I can do something with it, right? This X thing is just a data type, remember? So then I can, maybe compile that to some kind of other object code, and then, evaluate that, like interpret it or run it on a different device or something. And here I've written it as like, well, I'm going to execute this as part of my Haskell runtime, but that might not be the case, right? Like the Copilot DSL, it's generating C code to run on some different embedded device that runs on Mars or something, right? These might be very separated. But, and then the core problem there is like, well, if I'm thinking about how do I do this pattern match, right? The time that I know, should I take the nothing branch or the just branch, that's at a different time, right? So the pattern matching occurs at this host program runtime when I'm generating this AST, but I only know which branch I should take much later, right? When I'm running the embedded program, like presumably after I've already generated this code and compiled it and I'm running it, right? So there's this kind of phase distinction here, like this separation. And so this is this problem. Right. Okay. So this brings us to the final ingredient that we need, right? This match constructor, right? And so the key idea is that, so if we go back to this incomplete implementation of the maybe function, right? The key idea here is that we need to run this function twice. So I've written this with lambda case to give you a kind of hint, like this little lambda, we need to run it twice so that we can peek over onto the right-hand side and extract, if you give me a nothing, what should I do? And then if you give me a just, what should I do, right? So we need to run this function twice and supply some kind of argument to force Haskell's pattern matcher to succeed on each time, right? And so then once I get each of those separate right-hand sides, then I can kind of mash them together and build my embedded program and have an embedded case statement, right? So this is the key idea. Like, how do you run this function multiple times to extract all of the right-hand sides? Okay. So before I started by saying, okay, this is how we take our point data type and embed it into our language. But we kind of don't know what to do for some types. So if we instead go the other way, we can kind of use some intuition to figure out what we need. So we know we're going to need a pattern synonym of this type, right? So this is kind of the type of just, but I'm going to put exps around all of the arguments, right? So I'm going to take an exp of A and return an exp of maybe A. So for the builder, given an exp of A, we just need to record somehow that I want to treat this as a just A. Right? So this builder just has to wrap its argument in some kind of tag that says this was a just. And then the matcher has to do the clever thing. It has to signal to the host language Haskell somehow that this pattern match should succeed or fail, right? And return in X here some way to get the thing in the maybe out, the thing in the just out. Right? And so the key thing here, this is a just constructor at the Haskell level. So this is a maybe of type XA. And then because it's and then because it's on the right of this view pattern in the matcher, that's going to be the thing that signals to the Haskell pattern matcher whether to succeed or fail. Right? This is the trick. Okay. So we can do the same sort of thing, right? How do we embed this maybe data type into our embedded language, right? We need this representation type. So I need some kind of tag to record, is it a nothing or a just? And then I need the fields of each of the constructors. So nothing has no fields in it. I can just use units, and the just, I need to record that A, right? The builder, as I said, just has to take its argument X and kind of add some kind of constant or something to indicate this was a just, right? So here I'm just going to use words for my tags and say that a just is represented by a 1. It's fine. And then combine that with the fields, right? So the argument X, right? So I'm just taking my argument X and wrapping it in a tag that says this is a just now. Yeah. The matcher is the interesting thing here, right? So the matcher is here. Now we take an expression of type maybe A, and I return a Haskell maybe of type XA, right? So this is an embedded expression returning a regular Haskell value. This is the kind of time traveling part. Yeah. And then inside that, like if I get a just, then I get some expression that tells me how to extract the value from my embedded maybe. Yeah. And so the trick here is that we need to inspect the argument somehow with this sort of special value, right? And so this thing is saying that if I'm looking for a maybe, like I'm trying to peek under the right-hand side of the just case in a pattern match, then you should return this thing, right? And then signal to the Haskell pattern matcher that like, yes, I'm interested in looking under the right-hand side of the just case in my pattern match, and now you should continue. Yeah? But if I'm not interested in peeking under that just constructor, right, then I can just return nothing, right? And that tells the Haskell pattern matcher, like, no, this didn't succeed. Yeah? So we're not, the key thing is we're not inspecting the actual value A here, this actual term, because I don't know what that is yet. I'm just inspecting this kind of special thing that I'm wrapping my terms up with. All right. Yeah. So if we go back to the implementation of this maybe function, right? If I'm going to implement this manually, right? Basically, I need to evaluate this function twice, get the left-hand side out, the right-hand side out for the nothing case, and the right-hand side out for the just case. So you do this, right? So you call this maybe function, but now I've wrapped this argument P in this special thing that says, I'm interested in peeking under the just case. Yeah, so match here is this dummy argument that's going to be consumed by the embedded pattern synonyms, and this trace is just this thing that's telling us which are the constructors that we're interested in looking at. Yeah. You do the same thing for the nothing, right? And now that I have both of the right-hand sides, I can build this embedded case statement that has the right-hand sides for each of those, right? Just kind of put it all together. That might seem like a lot of work, but you can automate the process a lot with this single function called match, right? So it has this funky type, f, and it just sort of goes along each of the arguments, and for any argument that has a sum type does this procedure, right? So with this function, and you have these two instances, and that's enough to kind of do it, right? So then I can take this almost working implementation, and I just sort of slide that case statement over a bit, and add this magical match function. And so that's enough. So this works now. Yeah, so that's the core idea of the work, right? There's a lot more details in the paper. How do you handle recursive data types or nested pattern matching, or things like maybe bool, for example. Lots of details, including the implementation of this magical match function, but actually, in the end, it's short enough to fit on the slide, but we're not going to go through all the details. Anyway, so this is how we've figured out how to support user-defined algebraic data types in an embedded language, but also capture the pattern matching from the host language and lift that into the embedded language. And we have a few implementations on GitHub if you're interested. So, thank you.